Welcome to a new test and teardown video. This is another homebrew equipment from Jørn's collection. I believe this is a frequency counter, and the front here is made using CNC machines, I guess, because look at that. How can you make a hole like that? And how can you drill all those holes? We got a little bit of dust here, but how can you drill them this accurate if it's not done on a CNC? So I think he used the hardware lab at Storno, where he worked, to make this nice front plate. Also, if you check out this case, this is a Storno case, and the reason I know that is because I got this one, and that is a Storno product. This is exactly, oops, don't want to scratch this one. This is exactly the same case. And they're very easy to use. All you have to do is pull them out, and then you can rebuild something else into these cases. Let's look a little bit on the back. So here's how it works. You just unscrew those two, and then you can pull out the entire instrument. Let's try and do that. I believe this case came in many different variants, holes and stuff on the back. It looks like these holes here, they were actually here already, because you can see the painting. So Jørn chose to put this, I think this is a regulator or a power supply part, in that hole, because of course this is better. And there's also a BNC on the back. I mean, we got the two inputs here on the front. Maybe that is a clock reference input. So now we are inside, and let's try and power it up. Ooh, 20 watts. Really? It seems to be working. One of the 7-segment LED displays is like replaced with another type. That is of course visible. I would probably have put this to the far left or the far right. So let's try and input something. I am an LF. What do I do here? I don't know. Oh, what did it do? Something happened. What did we do? Okay, here we go. So it takes, of course, 1 second. Aha. And then what? Okay. So now we are running in 0.1 second. And this is 1 kilohertz. We got something that is blinking here, I guess. Yes, it's blinking. Okay, so the gate time. Maybe this is... Yeah. That was me. Okay, let's go back. 1 second gate time, and then a very short delay time. Okay, now I got it. Okay, so this is 1 kilohertz. Let's try 2 kilohertz and see. Then next time. Yeah. Okay. So that kind of works, right? So that was then LF mode. So that means if I go to 10 seconds, I will get a decimal on my 1 kilohertz. So that is pretty cool. I'll try and experiment with the frequency range for LF and VHF. So we're still in LF mode, and this is 1 megahertz. And see what happens here if I go to 2 megahertz. Okay, no problem with that. 3, 4, 5. I think so that's 8 megahertz. It's handling easily. So, but 9 megahertz, and then we get this. So I mean, this is maybe like an overload or a warning that you're getting too high for LF. I think so, right? So that means I should put this. And switch to VHF. And then what happens? It's not reading my 9 megahertz. What am I doing wrong here? Okay, so here's the thing. We go back to LF, and then I just hit the 0.1 gate time. And then I can, of course, see my 9 megahertz. I can probably also carry on. So this is 10 megahertz. And I am absolutely impressed. How can this thing be that accurate? Okay, this is 10 hertz. Right, so I think we're gonna let it overrun and see the last one here. Maybe it's possible to overload it even more, right? So that is 0.1 of a second now on the last one, and it's just going to overrun. So let's have a look. This will take 10 seconds. I'm sorry for that, but that will be the gate time to get the last digits. Okay, so this is 1 second, and this is 10 seconds. So that is actually quite impressive. I guess there is a free running oscillator in here somewhere. Of course, we're going to have a look and see what's in there. So this is 10 megahertz, okay. 20. I'd like to see the range for the LF. Let's just crank this up and see what happens. Oops, and then it goes out. So, okay, 50 megahertz. Let's see if we can do 51. Yeah, okay, we can probably do like 55. Yeah, easy. And then it, okay. So then, okay, it's doing 55. So this is what I'm gonna write down. The LF goes from 1 hertz to 55 megahertz. And then I just took the 55 megahertz into the VHF, switch to VHF. I think there's a divider, because now you see, got 10 hertz resolution here, and we're still gating 1 second. So that's how it works. And then we can crank up the frequency. And then let's see. So that is 100 megahertz. Yes, exactly. Good. So that is 100 megahertz. I would have loved to see like a dot here, or moving dot for megahertz or something. Then it's easier to see where you are, right? So that is 100. Let's just see if we can go 200. Yeah. 4. Ooh, that is not VHF anymore. 500. What? I need to go and get another generator, man. Hang on. So I figured out this one is a count up enable, so you can see the count up. And this one is a hold. And by the way, it is much better with 400 megahertz. I can't actually make it read 500 anymore. So I think it's something went a little bit hot. 450, 480. Okay. Let's see. Nope. So 490 is the limit at the moment, but it was actually 500 when it was colder. it is using 19 watts. So I mean, this gets very, very warm. There's also something else that gets warm here. Ow. Let's look inside. Of course I figured this out. So there's a BNC connector on the back, and that is 10 megahertz input with auto detect. That is pretty cool made. So how did I figure this out? Well, by looking at this IC and how it was connected. Yeah, so that's definitely how it is, and that is so smart. So what I did is, this is 100 megahertz in here, and this one is connected to another one of my generators. So, and this is 10 megahertz input, but this is now 10.1 or 9.9. So I can trick this unit to run slower, and then it will of course read more. That is of course how it works, but this just proves that it's now running on external, and if I pull the BNC, it's gonna jump to its own frequency. Isn't that cute? I'm actually a little bit impressed about this design. And it's all made in more or less flying leads and mini mount. I think this is an older version of mini mount before it became mini mount. So this is of course the oscillator and the swap over is done right here. So this is the main counter section. We've got 7 counters, 7 latches, and 7 LED drivers. See how cute that is, with all those wires to the displays. I mean, there is a lot of great hours invested in this instrument. Yeah, so this is the power supply. I think we got 3 individual power supplies, right? At least we got 3 sets of bridges, of rectifier bridges, and that will be some op amps. But there's more. Let's look at the back side. Let's look at the bottom side is what I wanted to say. And now this acrylic fell out, and now I understand why this segment looks different. What? It's a green one. Oh no! I think I got this exact type on my stock. So with a little bit of luck, I can restore this to perfect condition. That will be something. Let me take this. So this will be the 2 inputs. Oh, let me turn off the mains. So this is an amplifier module, that black one. Oh yeah, this is a prescaler, right? And another counter. And what have we got here? We got a lot of counters again. Oh yeah, okay. All this is of course the time base counting. And that will be the logic for latching and readout and stuff like that, right? Yeah, those switches, they handle the different timings, how you select the different timings you want to use. I mean, it's very compact built into this case, and how he made this case so good and reusable. Oh, look at that detail. Drill some holes and stick in the aluminium like that. That is not a bad idea. Yeah, that's the same in the other side. Okay, so that is the trick to hold this place. Hold this plate in this type of case. Yeah, so that is how it's made. And by looking on the different date codes on ICs, I see a lot of them from 1974, and I also see a lot of them from 1977. Yeah, so all this is from 77. Oh, this one is from 80. But was it changed later? Was it this original? 75 and 76, and this one is also 76. I mean, yeah. So let's call this unit a 1975 to 1980. I mean, that is the best guess I can come up with. Now I need to go and look at my LED segments. Oh man, of course this is common anode displays, right? I just happen to have one of those. I actually got quite a few of those FND 500s, and they're exactly the same form, fit and everything, but they're common cathode, so obviously this is not going to work. So if I put in a more modern, I don't know if I'm able to do that with only one hand, but anyway, a more modern one with red LEDs. Of course this one is going to be, see, insanely bright. So by using this color, it will be dimmed by the acrylic film, and this is why it was done like this. I didn't stick it in all the way, but see, so the green one, see what happens, then it gets dimmer. Haha. But of course I wouldn't put it here, I would put it there then, because I need to go and find an old one. But anyway, so this is what I'm gonna play with the next hour. Thank you very much for watching. I hope you had fun. So that was FND 507, right? And that is a common anode. This is what we need for the 7.4 type drivers. Now I'm gonna put it in the middle here and take the other one to the right. So now it is assembled, and I'm super happy about the result. Of course, you can do this super stable. I am a little bit cheating here because I'm using external input. And both signals are coming from the same dual output generator. Otherwise it's not possible to make this stable. Let me show you if I remove the reference signal. Of course it's not going to stay like that, right? It's actually quite stable. See? Now it's changing a little bit.